Okay, moving on to the yaw control system now. So yaw control is achieved by a hydraulically actuated rudder hinged on the rear spar of the vertical stab. Movement of the rudder is controlled from the conventional rudder pedals, which are cross-connected through a system of push-pull rods, levers, quadrants, cables, pulleys, and bell cranks running under the floor, down the left-hand and right-hand side of the cabin under the floor, and up the vertical stab to the rudder. That transfers the inputs to the PCUs, of which there are 3, powered from one each of the hydraulic systems. Secondary input to the rudder control system enables inputs from the yaw dampers and the rudder trim system. And rudder trim is provided by an electrically actuated trim system controlled by the rotary trim switch on the center pedestal, which repositions the neutral position of the rudder. So the yaw control system has 3 independent PCUs plus a duplicated control circuit, which includes 2 anti-jam breakout mechanisms. So if there's a jam in the circuit, the system kind of automatically will break out. There's no disconnection device like there is in the roll or elevator circuits. So these anti-jam things provide a means to overcome the effects of a jam circuit, enabling control to be maintained through the cable run, which is unjammed. We have 2 feel mechanisms, primary and a secondary, that provide artificial feel at the rudder pedals and act as centering devices for the rudder control. In addition, the secondary mechanism suppresses control system backlash, providing pilots with more responsive rudder control. 2 yaw dampers supply small rudder corrections in response to signals coming from the IRUs through the FCCs. They function together with 2.5 degrees of authority each, up to 256 knots. At that time, yaw damper 2 will center and deactivate. The yaw dampers aid turn coordination and eliminate undesirable yaw excursions that could lead to the onset of Dutch roll. And we'll look at that in more detail a bit later on. The primary fill unit, and remember there are 2, there's a primary fill unit and a secondary one. The secondary one is towards the back end of the control run. The primary fill unit is located forward of the co-pilot's rudder pedal assembly, and basically is just a centering cam and a spring-loaded roller that rides up and down on the cam as you push the rudder pedals, giving us our artificial fill. And this cam and roller also act as a centering device to center the rudder pedals. But there's only one of these, it's on the co-pilot side, but since the pilot and co-pilot's pedals are connected, they will both receive the fill input. So a lower bell crank on each rudder pedal assembly translates this pedal movement into a fore and aft movement of a push-pull rod, which is then connected to the forward cable quadrant. Cables on the forward cable quadrant transmit the movement of the cables down through to the aft cable quadrant. And on the forward cable quadrant, you've got the anti-jam mechanism. There's one on each side. So should one cable run become jammed, the anti-jam mechanism allows the other cable to continue to operate. A cross-coupling cable synchronizes the movement of both the pilot-co-pilot's breakout mechanism. By adjusting the bell crank pivot point on the free quadrant, it increases its movement, thereby ensuring that the degree of total rudder movement will be unimpaired when it's jammed. So the rudder will still have full and free movement. It's just one cable set will be jammed, and the jam mechanism is breaking out, allowing the other side to still move. Here we can see 3 sub-assemblies, A, B and C. A is at the bottom, B is in the middle, C is at the very top. So the inputs from the pilot rudder pedals come along and they're inputted into the rear cable quadrant. That changes into a push-pull rod, which we can see in item A, the control rod, where we have the rear anti-jam mechanism and a load limiter. and in fact 2 load limiters really, a small one and then a larger load limiter rod. So the input movement is transmitted along to the long load limiter via the secondary fill mechanism, and then it comes up to detail B. So the load limiter rod is moving up and down with the pilot inputs, and that will make an input onto that upper or the center bell crank lever, and another bell crank where the 2 yaw dampers are attached. Then there's like a walking beam at the bottom of the 2 yaw dampers, and in the center of it is the trim actuator, which is fixed at one end to the aircraft structure. So when the load limiter is moved up and down, that center bell crank moves, and that's going to make an input into the control rod, which then goes up to the upper bell crank lever, which we can see in detail C. So that control rod moves up and down, which translates to a horizontal push-pull rod that's connected to the PCU input torque tube. And when we move the PCU input torque tube, it moves servo valves on the PCUs, which drives the rudder backwards and forwards, and then there's feedback from the rudder to null out the PCU input. When the yaw dampers operate, they can operate singly or they can operate in pairs. It depends on the airspeed. When they move, they place their input onto that outer bell crank lever, which makes an input into the control rod, but that movement or that input is not felt back along the load limiter to the rudder pedals. So when the yaw dampers are working, the rudder pedals do not move, and it's the same for the trim actuator. When the trim actuator is operating, the rudder will move, of course, but not the rudder pedals. A dual 26 volts AC rudder position transmitter is installed at the bottom of the vertical stab rear spar. One winding supplies an analog input to the DCU, which is then digitized to generate the position on the ICAS, flight control synoptics, and the other winding provides an input to the flight control computers of the autopilot system. Here we can see the rudder trim selector switch, which is a rotary switch spring-loaded to the center position with nose left and nose right selections. And in the lower part of the picture, you'll see the rudder trim actuator and also the yaw dampers and the input rods from the rudder pedals and the output rod going to the PCU. And you can probably see a better view on this picture as to why when the yaw damper moves or the trim actuator moves, it doesn't move the rudder pedals, but it does move the rudder PCUs. So basically, if the yaw damper moves or if the trim actuator moves, it's going to extend or retract and operate that yaw damper trim mixer assembly that's identified as yaw damper trim mixer assembly on the picture. It's going to make an input into that idler lever, but the idler lever is going to, the fulcrum of the idler lever is going to be at the top of the input rod from the rudder pedals. So it will cause the idler lever to move up and down, pivoting at the where the top of the rudder pedal input rod is, making the output to the rudder PCUs, but it won't move the rudder pedals. If you move the rudder pedals, it's going to move the input rudder pedal rod, and now that idler lever is going to pivot around the center position. So it's going to not affect the yaw damper or trim, but it will obviously move the rudder pedal output rod to the PCUs. Trim position is sensed by a position sensor within the rudder trim actuator. So as a rudder trim actuator extends or retracts, that as a signal from the sensor in there goes to the DCU and gets presented on the ICAS primary page at the bottom of the where the trim information is there. You can see rudder and a horizontal line, and there's an arrow there that moves left or right. There are 2 independent sets of spoilers on the 604. flight spoilers and ground spoilers. So the flight spoilers consist of a single panel hinged to the upper surface of each wing. And if you look at the picture there, you'll see two panels on each wing, an inboard panel and an outboard panel. The flight spoilers are the outboard pair of panels. They are operated from systems 1 and 2, hydraulic systems 1 and 2. So as you can see from the picture, each panel has got two actuators operated from systems 1 and 2, and they're mechanically controlled from the flight spoiler lever located on the center pedestal just to the left of the throttle levers. So when you pull that flight spoiler lever, there's mechanical control run that runs from there down to the flight spoiler PCUs. The flight spoilers can be deployed up to a maximum of 40 degrees in flight or indeed on the ground. The ground spoilers consist of a single panel just forward of the inboard flap, so it's the inner pair of spoiler panels, and they're electrically controlled by the PSEU and hydraulically operated just with a single actuator from system 1. The ground spoiler system is selected with a switch labeled ground spoilers on the left side of the spoiler lever, and we'll look at the logic as what causes them to deploy, but basically it's fully automatic and they deploy only on the ground. The ground spoilers are only deployed on the ground, and either automatically or indeed from a signal from the spoiler lever as well. We'll look at that later. Ground spoiler positions are either 0, fully stowed, or 45 degrees, fully deployed, and there's no intermediate position. They're either in or out. Flight spoiler and ground spoiler position indication, as well as all the caution messages and so on, are displayed on the ICAS flight control synoptic page and the primary or status page as applicable. So here we can see the indications on the flight control synoptic page. So we can see our spoiler panels in a box on the wing, and then as the spoilers deploy, an arrow line moves up and down, and there's like a tick mark at the full extent when it's fully deployed. We can also see our spoiler lever there, a flight spoiler lever. The flight spoiler indication is also repeated on the ICAS secondary page at the very bottom of the screen, and obviously warning and cautions on the ICAS primary page. The only thing this picture doesn't show is the ground spoiler control switch, but we'll take a look at that in a second. But there's a ground spoiler switch, but that switch basically arms or disarms them. The flight spoiler lever has got 9 detents with position markings at 0, 1/4, 1/2, 3/4 and max, which those markings correspond to the following angles. So 1/4 is 5 degrees, 1/2 is 16, 3/4 is 28, and max is 40. The lever assembly also includes a micro switch, which provides an output to the ground spoiler system. Remember, the ground spoiler system is completely electrically controlled. So there's if we look at the picture, you've got the flight spoiler lever in the cockpit, and underneath that there's some cables that run down to the control valve for the flight spoilers down towards the main landing gear wheel well area. And then the control run goes out to where out along the wing trailing edge to where the PCUs are. There are a series of detents in the handle to prevent inadvertent movement, so you have to overcome those detents to allow the handle to move. That just stops accidental movement of the lever. So from the spoiler lever, the command is sent and transmitted via push-pull rod to a lateral shaft, which in turn transmits the command to a forward cable quadrant. From there, the cables run under the floor to the aft cable quadrant, and then from there out to the PCUs. So when it gets to the PCUs, we'll find ourselves with a load limiter. This is basically just a spring strut, and it collapses or expands to protect the cables if the cockpit lever is operated without any hydraulic pressure being available at the PCUs. There's something called a 20-degree detent mechanism. This is installed on the rear spar outboard of the two PCUs, and it's there to prevent a dangerous asymmetry happening in the likely event of a disconnected input shaft or linkage when the spoilers are deployed more than 20 degrees. So how it works is the PCU control valves are actually spring-loaded to the retract position, and the spring-loaded detent mechanism supplies sufficient force to the input linkage to secure it in a detent at 20 degrees of deployment. There's a micro switch on each mechanism that provides a signal to the DCUs to confirm the serviceability of the 20 degrees mechanism when the aircraft's weight on wheels. Each flight spoiler surface is actuated by two PCUs. They're both identical and they're both same left and right. The inboard PCUs are powered from hydraulic system 1, outboard PCUs by hydraulic system 2, and each actuator is connected to the spoiler by two links. Position of the spoilers is indicated on the ICAS status and also the flight control synoptic page, as we saw earlier, and that is picked up. That position is picked up by a position transmitter mounted on the rear spar. The transmitters, which use 26 volts AC, provide the signal to the IOPS and IAPS via the DCUs to generate the applicable position display. And as we saw earlier, that display is in the form of arrows which move from the spoiler symbol or box to a mid or max deploy limit line, depending on the deflection. As long as the position is valid, the limit lines are displayed. The arrows are removed as soon as the spoilers are fully retracted, and all you'll see is just a box representing the spoiler panel on the synoptic display. Okay, looking at the CAS messages then, so we have a config spoilers red warning message associated with a config spoilers voice message. That will come on if any of the spoilers are deployed during the takeoff configuration when we advance the power levers, if they're deployed. The flight spoilers deployed caution message, that will come on for three reasons. Number one, if the spoilers are deployed with a rad out of less than 300 feet, or if the spoilers are deployed but the rad out signal is invalid and at least one gear is down and locked, or if fan RPM is greater than takeoff N1 with spoilers deployed and weight off wheels. Obviously the idea behind the spoilers is to slow the aircraft down, and if we've got a high power setting, there's kind of a conflict going on there. The crew are asking for more speed, and yet at the same time they've got the spoilers deployed to try and slow down. So the system's saying, hey guy, what the heck are you doing? You know, your spoilers are deployed and yet you're asking for more speed. The flight spoiler caution message, that basically means that will come on if there's no hydraulics available, because obviously they're not going to work. It will also come on if the detent that we talked about just earlier, if that detent system has failed. But you'll only see that if that detent has failed, that's only monitored on weight on wheels. So very simple control system. We pull the flight spoiler lever. That mechanically operates a control valve which ports hydraulic pressure to one side or the other of the actuator. As this spoiler moves, the control valve is basically nulled out, so the spoilers stop at our commanded position, and it's as simple as that. Okay, so now we're going to look at the ground spoilers. So the ground spoilers are the inboard pair of panels. They're operated automatically and electrically. although we can operate them manually as well. But even if we're operating them manually, it's still electrically controlled. The main brains behind it all is the PSEU, the proc switch electronic unit. We've got a single actuator on the panel, on the inboard panel, this time not two. And here we can see on the picture the ground spoiler switch that we were talking about earlier on. And it's got an armed auto and disarm position. So in the left wheel well, there's a ground spoiler manifold that gets the electrical signals to control the spoilers to deploy them or retract them. On the actual spoiler panel itself, there's a single actuator that receives hydraulic pressure from that control valve to extend or retract the panel. Remember, with the ground spoilers, they're either fully open or fully closed. There's nothing in between. We will just go through a basic overview of the system, how it works, and then we'll look at the nitty-gritty. But the ground spoilers are normally deployed automatically upon landing or during a rejected takeoff. For normal flight operations, the spoiler control switch is in the auto position, and the ground spoilers will automatically arm when the thrust levers go greater than the minimum takeoff position and the wheel speed exceeds 16 knots. So for these ground spoilers to deploy, one of the things we must have is an arming signal. They must be armed. And we'll look at it a bit later, but the arming signal can be generated automatically, like it is here. So the switch is in the auto position, and then you advance the power levers, and then the wheels have spun up. Or you can generate the arming signal manually by putting the switch into the arm position. Remember, the spoiler switch has got armed, auto, and disarm. So you must have an arming signal either generated automatically or manually yourself. So upon landing, the spoilers deploy when the thrust levers go to the idle position and either the inboard wheels have spun up or it's indicating weight on wheels, or the outboard wheels have spun up, or weight on wheels channel 2 is indicating weight on wheels. That's all sensed by the PSEU. The ground spoilers deploy and then they will automatically stow 3 seconds after the aircraft slows down below 16 knots. So remember, before anything happens, they must be armed. So we were talking before about auto arming. So the auto arming is where you advance the power levers, first tick in the box. The aircraft begins to roll, it goes above 16 knots. That's the second tick in the box, now it's armed. Now, if you pull the power levers back to idle, they will deploy because it's a rejected takeoff. Or you take off, and then when it lands, weight on wheels, or the wheels spin up, a power lever back to idle, they will also deploy. There is also an arm position on the switch. Now that's manually arming it. So when it's manually armed, deployment will occur if the power levers are idle or below, and the weight on wheels or the win up, spin up requirements discussed above on the previous slide are met. So this method is the usual method for deploying the ground spoilers on the ground for maintenance purposes. You just put the switch in the arm position, make sure the power levers are at idle. Another method to deploy them on the ground while stationary is to select the auto position on the spoiler switch and pull the flight spoiler lever to call to travel. This actuates a switch in the flight spoiler quadrant which arms the ground spoilers, and if the deployment conditions above are satisfied, the ground spoilers will deploy actually as well as the flight spoilers. When the flight spoiler handle is selected to the stow position, both the flight and the ground spoilers will retract. So all of that logic can be summed up in this logic diagram here, which we're going to go through now. So there's two logic diagrams, this one, which is the deploy logic, and this lower one, which is the retract logic.
So let's go through the deploy logic first. So here's our deploy signal. If we get a 1 out of this AND gate here, they deploy. So to get a 1 out of this AND gate, we need a 1 there, and we need a 1 there. So the first thing what we said is we must have an arming signal. Now the arming signal can either be automatically armed, or it can be manually armed. And this is an OR gate, so we get a 1 there or a 1 there. We're going to get a 1 out of here. That means we just need to wait for a 1 to come through to this line here, and then they deploy. Auto arm, let's look at that. When do we get an auto arm signal? So we follow this AND logic here. So left thrust lever is more than takeoff, right thrust lever is more than takeoff, and both wheel speeds are more than 16 knots. So in other words, we apply power using both power levers to the takeoff position. The aircraft begins to roll forward. Once it gets to 16 knots, boom, we have a 1 there. This is an AND gate, so we need also a 1 here. That 1 will come by having the arming switch in the auto position. So the arming switch is in the auto position, boom, boom, boom. We apply both power levers to the takeoff position, and the wheel speed is more than 16 knots, boom, boom, boom. That means we've got our auto arm signal, which comes to there. This is an OR gate, so we got a 1 there now. We've got a 1 there, sitting there, ready to go, waiting for another 1 to come in from this bottom. So when does it deploy? Well, we know it's going to deploy if there's a rejected takeoff, and we know they're going to deploy automatically when it lands. So if we've already armed it, if the power levers now go back to idle, both of them, we get a 1 there, and we're still weight on wheels, but more than 16 knots, so it's just using 2 channels here. So weight on wheel channel 1 is weight on wheels, or we're greater than 16 knots. Weight on wheels channel 2 is weight on wheels, and we're greater than 16 knots. Boom, boom, boom. We've got a 1 there. We've got a 1 there. We've got a 1 there. So they deploy. So it's going to deploy. If you look at this and you think about it, that will cause them to deploy for a rejected takeoff, and also once it's land. Because that arming signal stays valid. Once it's armed, it's armed. On the auto arm side of things, once it's armed until basically it deploys, and then it starts all over again. So that will cause them to deploy either for a rejected takeoff, because we bring the power levers to idle and we're still weight on wheels, so all this logic is met. Or we go flying and then we land, so the power levers will be at idle, the weight on wheels is all accomplished, plus the wheel speed, and they deploy. So they've deployed. We've deployed them now. Now, of course, we want to retract them as well. We don't want them stuck out. So we go down to the retract logic. So what's going to cause them to retract? Well, obviously, if we put the power levers more than idle, if we do a go-round, for example, and we put the power levers more than idle, that will cause them to retract. That's a go-round retract. Once the inboard wheels and the outboard wheels are below 16 knots, and the deploy logic has already been accomplished, and we're weight on wheels for 3 seconds, once all that's happened, that will auto-retract them. Or there's a manual retract. So the spoiler switch, we disarm it because we've no longer got an arming signal. The flight spoiler goes to less than a quarter to position. This part of the logic was only applicable if the spoilers were armed with the flight spoiler lever. Remember, that was one of the things that we can cause them to arm. It was one of the methods of manually arming them. We either have the spoiler switch in auto, or and these flight spoiler lever more than a quarter. that causes a manual arm signal as well. There's two ways of getting a manual arm signal. One is you have the spoiler switch in auto and the flight spoilers more than a quarter position, or you put the spoiler switch in the arm position. So once it's deployed, to auto retract them, it's looking for them. They obviously must be deployed in the first place, so that's the first thing. And then weight on wheels and wheel speed input goes below 16 knots, so they automatically retract. Or manually retracting them, you just switch the spoiler switch to the disarm position. That will manually retract them because you've no longer got the arming signal as one of your things. Or you put the flight spoilers back to less than a quarter, as long as they were armed in that method. So that's the deploy and retract logic.
So once all that logic is met, and we've decided, or the system's decided it's going to deploy them, and remember the thing that's processing all of this logic is the PSEU itself. Once the PSEU is happy that he wants to deploy them, then he will send a signal to the control valve in the main landing gear wheel well, which contains two solenoids, and both solenoids will need to be energized for them to deploy. So on the control valve you've got two solenoids. They both have to be deployed, or energized I should say, in order for the ground spoilers to deploy. Okay, moving on to the flap system then. So with the flap system we've got two flap panels on each wing, an inboard and an outboard pair, and they're driven electrically with two electric motors by a power drive unit which is in the main landing gear bay with a flexi drive shafts running out along the trailing edge of the wing to drive screw jack actuators on the flap panel. So we've got two AC powered flap motors attached to a power drive unit gearbox, two screw jacks on each flap panel, and flexi drive shafts to drive the system. The flap selector lever is in the cockpit, just to the right of the throttle levers, and we can make a selection of 0, 20, 30 or 45 degrees. The flap selector lever is an electrical switch, operating switches at those set positions that send a signal to the flap control unit, which is in the avionics bay. The flap control unit, which is in the avionics bay, provides 28 volts to operate some extend or retract relays, which determines the direction and operation of the PDU motors. And also the flap control unit will monitor the system for any malfunctions, and if it detects anything, it's going to basically lock the flaps down and they just stop working. The flaps themselves are the double slotted type. Each outboard panel has a fixed leading edge vane, and each inboard panel has a movable vane which extends and creates a slot when the flaps are deployed. On the cockpit, on the ICAS primary and the flight control synoptic page, we can view the position of the flaps with an analog and a digital readout. The flap control unit has two purposes really. One, to receive the command inputs and left and right flap speed information, and provides the flap status information to other aircraft systems that need that information with extend or retract commands to the PDU. So let's just walk through this schematic. So at the center of the system really we have our flap electronic control unit that is in charge of the flap system, is going to control it. And it's going to receive electrical command signals from the flap selector lever in the cockpit, and it's going to compare that signal with the position signal from the flaps. And if there's an error, it's going to try and null that error out by driving the flaps either up or down, and it does that by controlling the motor relays to operate the motors. We've got a flap power and drive unit, which is basically a gearbox with two motors Normally both motors will operate together, but if one motor has failed or is not working, the other motor will carry on as normal, but in that situation the flaps operate at half the normal speed. Each motor has an overheat sensor, and if the motor overheats, that motor will be isolated and switched off temporarily until it cools down, and the other motor will carry on, and obviously in that situation it's going to go at half the normal speed, or the flaps go at half the speed. The motor will drive at the same RPM actually. It's just through the gearbox you end up with half the normal output. Once the motor has cooled down, the other motor will then be reinstated. And that's the only time when, during a failure situation, the system automatically kind of resets itself. For any other failure, the flap electronic control unit will basically disable the flaps, and you have to do a reset procedure to get them back online. Power supplies, we need DC and AC. DC bus 1 and 2 for the control unit, and AC bus 1 and 2 for the motors themselves. We've got on the drivetrain at the outboard side, we've got a detector brake unit. So the brake unit contains a brake, so once the flaps have reached their position, the brakes are applied, and that just locks the flaps in that position. And the detector unit detects RPM of the system, and also direction. And the flap electronic control unit will compare the left and right detectors to make sure the motors are turning at the same speed in the same direction. And if they're not, then obviously that's going to lead to an asymmetry, and then the flap electronic control unit will shut the system down. The flap position for control purposes is sensed by a flap position sensor on the gearbox itself, and that will feed into the control unit. Now that flap position on the gearbox is only used for control purposes. For position information purposes, there's some additional position sensors that are not shown on this picture because they're used only purely for indication purposes and actually for information going to the stall protection computer. So here we can see the arrangement of our physical components. So we've got our flap electronic control unit in the avionics bay. We've got the flap control lever in the cockpit compartment. And when you move it, it moves that rotary switch assembly, which sends the signals down to the flap control unit. In the main landing gear bay, we've got our power drive unit with the 2 electric motors and a couple of flexi drive shafts that run out the drivetrain to the inboard and outboard panels on each side. And on each panel, there are 2 screw jack assemblies that drive the flaps up and down. At the very end, you've got your detector brake unit, which will contains a brake. And so once the flaps have reached their desired position, the brake is applied. The brakes are also applied in the motors, and that basically locks the flaps in that position. And then the detector unit detects the speed and direction of the flaps, and the FCU will compare that with the other side to pick up any asymmetric condition. On the inboard panel, you have a movable leading edge vane, so entirely mechanically operated. So as the flaps extend, the leading edge vane kind of pops out and creates a slot in the flap. The outboard panels, the leading edge vane is fixed, and so there's like a permanent slot in the outboard panel. The FCU is powered from DC buses 1 and 2, but these 2 supplies are parallel so that only one is necessary to control the system. The function of the FCU is to assess the flap extend and retract commands received from the control lever, and then operate the extend or retract relays to drive the motors, and then stop the motors when it reaches a desired position. So the signal from the control lever is applied to one of the 4 voltage comparators, which represent the 4 flap settings. So basically, when the flaps are not in the same position as the lever, the comparator will see an error signal, And the idea is the flap control unit will drive the motor to null out the error signal until the error is 0. When the error is 0, the flaps are in the correct position. And then the flaps will stop and the brakes will be applied. So as we said earlier, the flap position potentiometer is on the power drive unit itself. And whenever a malfunction is detected, a fault latch is set, which prevents the control unit from operating any of the relays. And the set fault latch provides a discrete input to the DCU, which will then display a fat fail caution message on the ICAS. This fault latch can only be reset by accomplishing the flap reset procedure, which we'll go through a bit later on. But the control unit also provides signal for the following other systems. We've mentioned a couple before, like GPWS and the stall system, but there's a couple of others. So the flaps not at 0 signal, which goes to the PSEU, and the hydraulic system, and we'll look at the reason for that when we look at hydraulics. The flaps not at 0 signal for the electrical system, that's to do with the utility bus load shedding. The flaps more than 30 degrees to the PSEU, that's linked in with the landing gear warning. And flaps not at 20 to the DCUs, and that's part of the takeoff configuration warning. The PDU, we have two drive motors which are powered from 115 volts from AC bus 1 and 2. So just bearing in mind then, in an ADG situation, we don't have power on AC bus 1 and 2, and therefore the flap system won't work in an ADG situation, which means we'll be making a flapless landing probably. So our landing speeds will be quite high. Mind you, that's probably not a bad thing in an ADG situation, because by having a high airspeed, we're able to maintain the ram air turbine at sufficient RPM to make it work. But although both motors are used excuse me, for normal flap operation, only one is actually necessary. However, when operating on a single motor, the operation for the flap extension and retraction is doubled. The flaps travel at half speed. Now, the motor in that situation, the motor that's working, will operate at the normal standard RPM. The reason the flaps go at half speed is because of the gearing design inside the PDU. It's basically like a sun and planet type gear, and with both motors working, it's kind of summed together, and with a single motor working, you get half the output. A bit like how a CSD works in a generator control system actually as well. The PDU also has two motor brakes, which must be powered to release and torque limiters. And plus there's also a brake unit, a brake detector unit on the outboard end of the drivetrain. When an extend or retract command is received, the internal brakes are powered to release them, allowing the motors to actually work. The motor shafts will operate to drive the internal gear train and provide the driving torque at the output shaft. There's an internal clutch assembly which will slip on initial speed up of the flap drive system. So the flaps kind of slowly build up speed. Should the output torque exceed the torque limiter setting, the limiter will apply and stall the PDU motors. When the flap control unit senses that no flap movement is occurring for 1 second, it will see that as a failure. It will fail the flap system and remove power from the motors. The flap actuators are the linear ball screw type, gimbal mounted on the wing rear spar and the flap hinges. There are two actuators on each flap panel. The ball screw circuits are dual for redundancy, incorporate ice scrapers and wipers to prevent freezing of the drivetrain. Rotation of the ball screw shaft causes the ball nut to translate along the shaft in the extend or the retract direction as directed by the rotation of the input drive. Out of all the actuators, only the left and right inboard flap actuators are identical. On the lower surface of the outboard panel, or wing surface really, there's something called a butte door. Now, butte is actually stands for bent up trailing edge, and it's a hinge panel that fills the void when the outboard panels extend to make a nice, smooth, aerodynamic airflow. So as the flat panel extends, the bent up trailing edge will start to lift up, and it's all controlled mechanically with a control rod linked into the flap movement. The boot door will bent up, which kind of directs the airflow and smooths the airflow out and directs it over the leading edge vane and the leading edge of the flap. This improves aerodynamic efficiency and stops turbulence. As the flaps retract back in position, the butte doors will lower themselves, allowing the flap to slot back into the gap and make a nice smooth lower surface when the flaps are fully retracted. There are two flap position sensors or transmitters, one in the inboard left hinge and one in the inboard right hinge. Only the right flap position transmitter supplies the signal for the cockpit indications. However, both left and right transmitters contain microswitches for 5, 25 and 35 degree flap positions, and they feed their signals into channel 1 and channel 2 of the stall protection computer. So here we can see our flap panels again, the inboard ones with a retractable vane that opens out as the flaps go down to create a slot, and the outboard ones where the vane is fixed, so the slot is there permanently. And also on the outboard one you can see the butte door operating cam. So this is what pushes the doors or allows the doors to open up or pop up when they're extending, and it pushes them down to allow the flap to slot in position when the flaps are retracting. So we said earlier, on a couple of occasions, we said that once a failure situation happens, the flap system is basically frozen and is locked out, and we can't operate it, and we have to do a reset procedure to reset the system and get it back working. The only exception to that rule is an overheat event. If it overheats, if the motor overheats, it resets itself. But any other event, we need to do a special procedure to reset it, and we're going to go through that procedure now. So the first thing to do really is obviously to rectify the fault. If you don't rectify the fault, as soon as you reset it and try to operate the flaps, if the fault's still there, it's just going to immediately fail again. So you need to rectify the fault first. Once you've done that, you now need to reset the system. So the first thing to do is place a flap lever between any two flap detented positions. So on the flap selector lever, you've got these detented positions that the crew put the flap lever in to go to that position. What we need to do is just put the flap lever in between any of the two detents. You then pull the two flap control circuit breakers to depower the flap control unit and then reset circuit breakers. And then put the selector lever back into a position, into a proper position. The flap should now move to the selected position. Each of the ICAS indication bars shows the flaps at the selected position. You then put the flaps at 0 and verify proper ICAS indications, and hopefully that should do the job. But the key thing is to have the lever initially in between two detented positions, pull the circuit breakers, then reset them, and then you can move the flap selector lever. So here we can see our various indications that we have displayed. So firstly position information, that's displayed on the flight control synoptic page and also on the ICAS primary page. You can see there's a horizontal sliding bar, and then above it, it gives you the flap position degrees position. You got that kind of repeated on the flight control synoptic page. The CAS message is then flap fail. So any failure at all, whether it's an asymmetry or anything like that, the flaps will stop working and you'll get a flap fail message. The config flaps is to do with the takeoff configuration, and the status message flaps motor overheat, that will come on if one of the motors is overheated. It's only a status message because the flaps will still work, although they'll be operating at half the speed. The clacker oral warning there is if the flaps, there's an input to the of the flap position going to the air data system and vice versa. So if they try and put the flaps down at too high an airspeed for the flap configuration, then they get a clacker sound just to warn them. But the flaps will still work. It's just a warning for the crew. Moving on to the stall protection system, this provides warnings, both visual, oral and active warnings on an impending stall, and it's controlled by a computer. So the warnings we give the crew as follows. So we give them a stick shaker, which simulates aerodynamic buffet. We automatically turn on the engine igniters at that point when the stick shaker goes. The autopilot will disconnect. There's an oral warning in form of a warble tone. 2 red stall lights come on the glare shield. And if the situation deteriorates, ultimately the stick pusher will operate, which gives a full nose down elevator input to try and reduce the angle of attack. Any malfunction with the SPS obviously are going to be displayed on the ICAS as caution messages. So here we can see some of the pilot's side of the components. So we've got the stall warning lights come on the glare shield, which we just mentioned. There's also on the pilot and co-pilot side a stall protection panel that allows the crew to switch off the stick pusher and switch the stick pusher on. And incidentally, because of the way the system works, it's a 2-channel system, for the stick pusher to operate, both channels have to agree. So therefore, both channels have to be switched on for the stick pusher to operate. We've also got a stall protection test on the miscellaneous test panel. There's 2 switches there, left and right. Again, if you operate both switches, the stick pusher will work, but the stick pusher won't test if you only do one system. And also on the co-pilot pilot hand wheel, there's the master disconnect switch, which is usually used for disengaging the autopilot, but when you push it, will also temporarily disengage the stick pusher as well. Although, as far as I'm aware, that's only on FAA registered aircraft. For EASA registered aircraft, that part of the function doesn't work. The stall protection computer is in the avionics compartment on the left-hand side, and it's got 2 channels, independently powered from the battery bus and DC essential bus. And the idea of each channel is to assess the angle of attack, the lateral accelerometer information, plus looking at flap position information and altitude information to determine what the stall threshold is, and then calculate at what point we're going to give the warnings to the crew. So as well as looking at the actual angle of attack, the protection computer is also looking at the rate at which the angle of attack is changing, so that it can give the warnings in good time. There's no point, if the angle of attack is decreasing at a very high rate, it needs to bring the warnings in earlier so we have time to react. We've got other inputs to the stall protection system, for example from the weight on wheel system, which will inhibit the pusher operation when we're weight on wheels, unless we're doing the test. And obviously it will only allow the system to be tested when we're weight on wheels. As we can see from those relays there, there's a test switch, and in order for the test input to get into the computer, we must be in a weight on wheels situation. So outputs from each channel of the computer include an activation signal to the stick shaker, and each channel can activate its stick shaker independently from each other. You don't have to have them both agreeing. And an auto ignition output to turn on the ignition system, and a contributing signal to the stick pusher. So what it means by contributing is that the stick pusher will need 2 signals, 1 from each channel. The angle of attack related warning trip points for the stall protection computer are biased in accordance with pressure altitude sensed by the two air data computers. So this is known as altitude compensation. Obviously, as the altitude increases, the air gets thinner and the stall margins become reduced. So on each side of the aircraft you'll find a couple of AOA vanes. They feed into each channel of the stall protection computer. So an electrical signal proportional to the measured angle of attack goes to the associated channel in each computer. And the AOA vane is anti-iced as well to stop it freezing up. The stall protection test indicator displays a compensated AOA vane signal of its channel as computed by the stall protection computer. They are located on the pilot and co-pilot side panel. They're like a gauge type thing and are used for system monitoring and also for test purposes. If anything goes wrong with the system, there's a whole list of them there. I'll let you read through it in your own time. But there's a whole list of them there. Any problem with the stall protection system, obviously we're going to go on the safe side and disable the system. So you'll get a stall fail caution message on the ICAS primary page. This message is also displayed when the pusher circuit breaker on the battery buzz is pulled or when either of the pusher switch is set to the off position. So red stall light is on the glare shield. There's one on each side and basically they're connected to their respective channels. So each light is controlled by its own channel. When either of the SPS channel outputs a push signal to the pusher, the audible warbler will also be enabled. So you're going to get the audible warbler whenever any channel decides he wants to push the stick. But for the stick to physically push, you'll need both channel signals. On the stick shaker side of things, there's a stick shaker on each of the control columns. Each one is connected to its dedicated channel, and each one can operate from its own channel, regardless of what the other channel's doing. They have different severities of shaking, so the stick shaker rate ranges from 50 to 100%, depending on the situation. So it gets worse and worse as the stall situation deteriorates. The stick pusher is an independent subsystem. The physical pusher is installed near the right-hand forward elevator quadrant. It contains its own electronic circuits, which will only activate the pusher when it receives a push signal from the two channels. It consists of an electric motor, a module, a clutch, and a capstan with a torque limiter. A cable looped around the capstan is connected to the forward elevator quadrant. So there's a flap position sensor, as we know, in the inner flap assemblies in the hinge on the left and right hand side, and each transmitter contains microswitches operated by a cam linked to the flap hinge. And as they pass the 5, 25 and 35 degree positions, the left and right position switches send discrete flap position information to the left and right channels of the SPS computer. And the SPS computer will simply use this information to gradually reduce the trip point, because obviously with the flaps extended, we can get for a lower angle of attack. If the flap position signal is lost, the channel affected automatically supplies an angle of attack trip point associated with the next higher flap setting. A failed flap switch is indicated by different readings on channel 1 and channel 2 of the SPS test indicators at the applicable flap setting. We've also got a G switch, which is located near where the TRUs are, near the pressure bulkhead. It cuts out the stick pusher if we are subjected to less than half a G, and this is going to prevent the inertia of the aircraft from carrying the aircraft into a dive after stick pusher activation. We can test out the stick pusher using that miscellaneous test panel. There is a separate switch labeled G switch test to do that. We've also got two lateral accelerometers. They're located in the avionics bay towards the back of the avionics compartment, and they provide a reference signal to each stall protection channel to compensate of AOA vane angles during turns, slips and skids. So there is a test gauge on each side of the pilot's instrument panel. So this indicates during a test, but it will also indicate the AOA effectively when we're flying, and this is how you can compare the two sides, the two AOA sensors. But so during a test, the needle will go to a temporary overshoot past the red. If the test is good, it will return to the red area, and if the test has failed, it sits between the red area and the blue area.